introducing.
So Parimal,
Okay, yeah.
Amit is introducing, so he
So,
wanted
yeah.
to start.
Maybe we can begin now, yeah?
Yeah.
Yeah, we can
Thanks.
begin now.
Yeah.
So, yeah. So, good evening, everyone. Welcome to the another session of the network seminar series hosted by Center for Network Intelligence at ECE and RBCCPS ISC. So, today's talk by Professor Nikhil Krishnan. He will be speaking on streaming codes for 3 nodes relay network and burst erasures. So, Professor Nikhil received the BTech degree in Electronics and Communication Engineering from Amrita School of Engineering, Amrit Puri campus in 2011, and the MA degree in telecommunication and PhD degree in electrical communication engineering from the Indian Institute of Science, Bangalore in 2013 and 2019. So he was a postdoctoral fellow with the Department of Electrical and Computer Engineering University at University of Toronto from 2019 to 2021. So from 2021 to 22, he was assistant professor with the Triple IT Bangalore. He is currently an assistant professor with the Department of Data Science at IIT Palakkad. So before we move on to the talk, we would like to request everyone to subscribe to our Google group for information on future talk. You can also visit our website for more detail from the chat box. Please do check. Finally, we request the online audience to keep your microphone silent for the duration of the talk. And for question, you can unmute yourself and ask directly or post in the chat box so that we can relay them. So over to you, Professor.
Yeah, thank you. So, so please feel free to interrupt me during any part of the presentation. Yeah. So, I'll be talking on streaming codes for 3-node relay networks with burst erasures. This is actually a joint work with Dr. Vinayak and Dr. Myna. So let me begin with sort of like informally defining what a streaming code is. So let's look at this figure here. So there's a streaming server and there's a recipient. So you can think of the streaming server as the sender and you have a recipient. And the sender is sending a stream of packets over a network to the recipient. So each rectangle here denotes a packet. So I'm naming them 1, 2, 3 like that. So I'm sending them over a network. So unfortunately, some of the packets are getting erased. So that's actually indicated by those shaded rectangles. So here, for example, packet 3 and packet 6 are getting erased. So recipient is receiving only 1, 2, 4, 5, 7, and so on. So these packet erasures or drops could be caused by multiple reasons, depending on the channel that we have. For example, it could be due to some network congestion. It could be due to fading in the case of wireless networks and so on. Our goal here is to basically communicate whatever data that we have. For example, in the case of this figure, we have a streaming server, right? So the streaming server wants to communicate all this streaming data with the recipient. But it needs to do so with low latency, high reliability, and high throughput. So I need to communicate with as least delay as possible. And I need to somehow tolerate all these packet erasures or packet drops. And I need to introduce as least redundancy as possible in order to make this happen, right? So I need to have high throughput. So one solution for such a setting will be the naive feedback-based retransmission, right? So if the recipient is seeing that some of the packets are missing, he or she can send a acknowledgement, for example, back to the streaming server. And depending upon that, it can the streaming server can attempt a retransmission, right? But that would naturally lead to a 3-way propagation delay, right? From streaming server to recipient, that will be 1 way. Then recipient to streaming server, that will be 1 more way. And then retransmission will take 1 more round. So there will be basically 3-way propagation delay. And such a delay may not be ideal for interactive multimedia applications, right? For example, let's assume that the streaming server and the recipient are sitting on two diametrically opposite ends of Earth, for example. So if you have like three-way propagation delay in such a scenario, if you run the calculations, even at light speed, it will be like some 200 millisecond. So such a delay might be too much for interactive multimedia applications. So what's the way forward? So what we can do is, instead of doing a feedback-based mechanism, we need to introduce forward error correction, right? So without waiting for any feedback, we need to do some FEC. We need to do some erasure coding. So coding schemes which are designed keeping this goal in mind. So that is, we need to achieve low latency, high reliability, and high throughput. Such coding schemes are referred to as streaming codes in the literature. So today's talk is basically about that. So what are some of the potential applications? So naturally, we can think of interactive voice and video, right? Virtual reality, multiplayer gaming, etc. So what's the common theme in all these applications? So the common theme, the common thread which is running across all these applications is basically the following, right? So in all these applications, we can see that there's a stream of packets which need to be sent from a sender to a receiver. It could be voice, video, data, whatever. And there's obviously the need for reliable, low latency communication. So let's get slightly more formal. Okay. So if you recall, the talk title was streaming codes for a 3-node setting. Okay. So before going into the 3-node setting, let's look at a more simplified setting, which is a point-to-point setting. So there is a sender, or there's a source and there's a destination. Okay. So the source wants to send some message packets to a destination. So that's the point-to-point setting. So the setting goes as follows. So there is a source which has message packets M0, M1, etc. Okay. And as you can see in the figure, so each message packet is of size K. Okay. So each message packet has size K symbols. Okay. It could be bits, it could be some other higher sized alphabet, depending upon the finite field that we are using. Maybe for simplicity, let's assume that these are I'm using F2, which means these are bits. So I have each message packet consists of K message bits. Okay. And so the source has message packets M0, M1. So this 0, 1 denotes the time index. Okay. At time 0, source has message packet M0. At time 1, source has message packet M1, and so on. And the source also has an encoder as indicated in the figure. So at time t, what's going to happen is the following. The source will produce a coded packet, let's say x of t. Okay. And this x of t will be basically a function of what are message packets the source has till now. Okay. So x of t will be a function of M0, M1 till M of t. And the coded packet is assumed to have n symbols. So there are n symbols. Okay. So the message packet is having k symbols and the coded packet is having n symbols. Naturally, n is greater than k. And also we assume systematicity. So the coded packet, if you look at it, so the initial k bits will be basically the message packet, and that will be augmented with a parity component, okay, P of T. So each coded packet consists of message packet along with a few of n minus k other parity bits. Okay, so that's the structure of a coded packet. So at time t, the source is going to send the coded packet. Naturally, the rate here is defined to be k by n because I have message packets which are of size k, And then I'm producing coded packets which are of size n. So k by n is the rate. And the destination basically receives a y of t at time t. Okay. So this y of t could be either x of t or it could be a star. Okay. So star is basically indicating that there's an erasure which has happened. So either there will be an erasure or no erasure. There's no error that we are considering here. So y of t is either x of t or star. And on the channel model, so what we are going to assume is the following. So up to B consecutive coded packets may get erased. Okay. So currently I'm discussing the point-to-point setting. Next, after discussing all this, we'll go to the 3-node setting, which is actually I'll be mostly talking about. But I need some elements from this point-to-point setting to explain whatever we are going to do in the 3-node setting. So that's why I'm going in detail even through the point-to-point setting. So the channel model that we are going to assume is a bursty channel model. So what might happen is that up to B consecutive coded packets may get erased. Okay. And there is also a stringent delay constraint. So at the destination, at time t plus tau, destination will try to decode m of t. So recall that at time t plus tau, destination might have received y of 0, y of 1 till y of t plus tau, right? So using all those received packets, some of them could be stars as well, right? So because there are packet erasures, so some of the yis will be stars. But regardless of that, destination should be able to decode m of t by time t plus tau. So that's the requirement that we have. So there's a stringent delay constraint, which is indicated in terms of the parameter tau. So that's the setting of streaming codes for the point-to-point case. So this is introduced in the paper by Emin Martin and Sundberg. So turns out that there's a very simple rate upper bound for this scenario. Okay, so it's denoted by tau over tau plus b. That's it. So recall that tau is the delay constraint and b is the burst length. So if you go to the previous slide, you can see that b is basically the maximum number of consecutive coded packets that may get erased. Okay, and tau is the delay. And rate is given by tau plus b. Okay. The way usually streaming codes are constructed. So if you recall the streaming code setting, as you can see that there's a stream of message packets coming in, right? M of 0, M of 1, M of t, like that. It's an infinite sequence of message packets coming in. And you need to produce coded packets on the fly, right? So X of t, which will be basically a message packet augmented with some parity bits, right? So it's not a block code setting per se. But luckily, there exists a technique to construct streaming codes using block codes. Okay, so that technique is called as diagonal embedding. It's a very simple technique, which was introduced in this paper by Martinin and Proth. So the idea is as follows. So let me go through an example. Suppose you have a 6-3 linear block code, a systematic block code. Okay, so since it's a systematic code, so if you have message bits M0, M1, M2, you can basically generate a code word which is nothing but M0, M1, M2, and then there'll be 3 parity bits, right? P0, P1, and P2. So now, how are we going to transform this to a packet level code, right? So the idea is very simple. So if you look at the coded packets in a diagonal manner, so each diagonal will correspond to a code word which belongs to this code. Okay, so that's the idea. So basically, so each column here corresponds to a coded packet. So this is code packet corresponding to time 1. This is coded packet corresponding to time 2, and so on. Okay, so the initial 3 symbols of each coded packet will be purely message symbols for every coded packet. And now, for example, this parity symbol, that will be basically, so this parity symbol along with this parity symbol and this parity symbol, that will be produced in such a way that the M00, M11, M22, P03, P14, P25, that is basically a code word, which is belonging to the block code. So that's the way in which you can generate these parity symbols. Okay. So the last 3 symbols of every coded packet will be basically parity symbols, which are generated in this manner. So if you look at diagonal wise, it's basically the code word. It's going to be a code word which is belonging to the code C. Okay, so this is basically the diagonal embedding idea. It's a very simple and straightforward idea. So here I have just filled in all the other symbols as well. So I have indicated multiple diagonals. Okay, fine. So that's about diagonal embedding. So which was basically talking about, given a block code, how can we transform that to a packet level code. Okay, so now recall that in the setting which is being discussed right now, we were talking about a point-to-point setting, right? Where there's a sender which needs to send packets to a destination, and there could be error bursts which are happening on the way. And we also said that the rate is upper bounded by tau over tau plus b. Okay, and if you go back to this diagonal embedding figure, you can see that the rate of the packet level code will be equal to the rate of the systematic code, right? Because for every 3 parity bits, you'll be taking 3 message bits, right? So it's going to be half in this case, for example. So now for the point-to-point case, so let's look at an example. Let's say b equal to 4, tau equal to 6. So now if you look at the bound, which I discussed earlier, what it was saying was the following: r is less than or equal to tau over tau plus b, which is nothing but 6 over 10, right? So this is the best rate that is possible. So if you are going by the diagonal embedding approach, so what we need to propose is basically a block code, which has rate 6 over 10. Okay. So Martin and Trott basically actually came up with a code which has dimension 6 and block length 10. Okay, so which will naturally have rate 6 over 10. So what are all the properties that we need out of this block code, this 10.6 block code, so that once we do the diagonal embedding, it will become a streaming code for the setting as we have just described, right? So let's say this is a code word. So M0, M1, M2, M3, M4, M5, and you have the 4 parity bits. And now, since I'm considering the parameters b equal to 4 and tau equal to 6, right? So now let's assume a burst duration, okay, which is of size b equal to 4, which is wiping out the initial 4 code symbols of this code word. So what we want is the following, okay? So here, the assumption is the following. The blue symbols are basically available to me. All the black symbols are not available to me. Why are P1, P2, and P3 not available to me? Because right now I'm looking at the decoding of M0, okay? And because there's a delay constraint tau equal to 6, I can go only 6 places after that. So I can go only till, so if I number like this, so 0, 1, 2, 3, 4, 5, 6, right? So 0 plus 6 is 6. So I can go only till P0. And moreover, M0, M1, M2, M3 are erased, right? So basically all I have is M4, M5, and P0 to decode M0. So I should be able to recover M0 using M4, M5, and P0. That's the first requirement I have. Similarly, Let's consider another burst. Let's say M1, M2, M3, M4. Let's assume that M0 is already decoded. And since I'm looking at the recovery of M1, I can go only till P1. Because again, if you count, so this is 0, 1, 2, 3, 4, 5, 6, 7, right? So 1 plus 6 is 7. So I can go only till P1 because of the delay constraint. And again, because there's a erasure burst, M1, M2, M3, M4 are not available to me. So basically using M0, M5, P0, and P1, I should be able to recover M1. So that's the requirement I need out of my code. So similarly, I can write a few more requirements. For example, another burst I'm considering. So here I'm talking about recoverability of M2. Again, due to the delay constraint, I can go only as far as P2. P3 I cannot consider. And because of the burst, M2, M3, M4, and M5 is unavailable. So using M0, M1, P0, P1, and P2, I should be able to decode M2. Similarly, I can have a few more slides on recoverability. Okay. So now, how to construct a code which satisfies this property, right? So Holman and Tolhuisen basically came up with an explicit construction, and that too over F2. Okay, so we don't need to go to any higher field. So we can just play with the binary field itself. So the construction is due to Holman and Tolhuisen, and we'll refer to it as the HT code. Okay, Holman and Tolhuisen HT code. So here I'll just explain the construction for this example case: b equal to 4, tau equal to 6. So the construction is pretty simple. It's basically like filling the matrix, the generator matrix. So here I'm providing a generator matrix for the code. Okay. So this is the generator matrix for the code. So what's the size of the generator matrix that we want? Recall that we are looking at constructing a code which has rate tau over tau plus b, which is 6 over 10. And motivated by this, I'll be looking at constructing a code which has dimension 6 and block length 10. Okay, so we are looking at a 6 by 10 matrix. So how to construct the generate matrix? So it's pretty simple. So we'll start with an identity matrix, so of size 6. Okay. So now some space is remaining here, right? So what will I do there? Again, I'll try to fill those space with an identity matrix. So I'll fill like this. Okay. So again, here is some space there. Sorry. Yeah. So again, here is some space here, right? So again, what will I do? Again, I'll fill that with an identity matrix. So again, there is some space, which I'll again fill it with an identity matrix. So basically, we are like filling with identity matrices, which are sort of like non-increasing in size, right? So this is basically the construction. It's as simple as that. So let's just quickly do a sanity check and see if whether this generator matrix is satisfying whatever constraints that we have, right? So let's go to the next slide. So this is the generator matrix which we have just come up with due to Hodman and Tolhuisen, okay, the HT code. So here I am talking about a burst erasure of size b equal to 4, which is wiping out the first 4 coordinates, okay? And I'm talking about recovering the 0th code symbol. So I'll be following the notation 0, 1, 2, 3 for the code symbols, okay? So right now I'm talking about recovering the 0th code symbol, which is basically corresponding to this column of the generated matrix. And because of the delay constraint, tau equal to 6, I can go only 6 places after that. So I can go only till this point. I can go only look at only this part, okay? And moreover, all the red columns are not available to me because of the burst duration. So basically the property I want is that all the blue columns, right? So the 0th column should lie in the span of these blue columns. Is it true? It's obviously true. Why? Because 1, 0, 0, 0, you can see that in fact lies in the span of the this column, and this column, right? So clearly that property is satisfied. So now let's maybe quickly check a few more other properties, right? So let's look at another burst erasure, which is starting at location 1. 1, 2, 3, 4 are erased. And I'm looking at the recovery of column 1, the code symbol corresponding to column 1. Again, due to the delay constraint, I can go only till this point. These things I cannot consider, right? The last two columns I cannot consider because of the delay constraint. And the burst erasure is basically wiping out all the red columns. The property I want is the following, right? The column 1 should lie in the span of all the blue columns again. Again, you can see that that's true. You can see that, in fact, this column, and this column. So if you take those three columns, column 1 is in fact lying in this span, right? So like that, you can do some sanity check and you can see that it's in fact satisfying all these properties. Okay, so that's basically the HT code. The reason why I was discussing the point-to-point setting and also the HT code, which will in fact result in an optimal code for the point-to-point setting, is that we are in fact going to build up on top of this HT code when I discuss our construction. Okay. So now it's time to finally introduce the 3-node setting. Okay, so far we have been talking only about the point-to-point setting where there is a single source and there is a destination, and the source was sending packets to the destination. Okay, what's the 3-node setting? It's simple. You have basically 3 nodes. There's a source, there is a relay, and the destination. Okay, so it is assumed that relay can do computations. Okay, so relay can receive packets from the source, can do some decoding and then forward those packets. Maybe it can create its own packet based on whatever it has received, do some computation, create its own packet and send those packets to the destination. So relay can do computations. That's the assumption. So again, let's sort of formally look at the setting. So what does the source have? So at time t, the source is having message packets M0 till MT. Okay. Again, as in the point-to-point case, I'll assume that each message packet is of size k symbols. Okay. So each message packet has size k symbols. And the source is now going to send a coded packet. Okay. XST. So S is for, sorry. Yeah. So the source is going to send a coded packet. So here, instead of simply XT, as in the case of the point-to-point case, I'll be introducing an XST because there'll be coded packets which will be sent by both the source as well as the relay, right? So in order to distinguish between them, I'll be using the superscript notation. So S stands for source. So each source will be producing a coded packet XST at time t. Okay. And the size of XST will be basically NS symbols. Okay. So the source will be sending the coded packet over to the relay. And what does the relay do? So relay will receive by RT, okay, where R for relay. Okay. So relay will receive a YRT, and YRT will be either the coded packet which is sent by the source itself, which is XST, or it will be a star, which is indicating an erasure. Okay. So there will be either erasure or no erasure. Again, there will be no errors. Okay. So YRT will be either XS of T or star. Again, as in the point-to-point case, we'll be assuming that at most B consecutive time slots, there'll be erasures. Okay. So stars are basically confined to within B consecutive time slots. All the erasures will happen within B consecutive time slots. That's the assumption. And what does the relay do? So relay will take all these YRTs and it will produce coded packets on its own. It will do some computations. So recall that the relay can do computations. Okay. So relay will do some computations on top of this YRT, the received packets, and then it will produce another coded packet, which is XR of T. Okay. And the size of XR of T is basically NR. So recall that the size of coded packet produced by source was NS, and coded packet produced by relay will be size NR. Okay. So what does the destination now have? So destination will receive a YDT. Okay. And this YDT will be either XRT, which is being sent by the relay, or again, it will be a star. Okay. So erasures can happen in both the links. In both the source to relay link as well as in relay to destination link, then there could be erasures. So whatever being received by the destination, which is YDT, will be either equal to XR of T or a star. Again, as in the case of the previous link, these stars are basically confined within B consecutive time slots. We'll be assuming a burst channel model where the burst has length at most B. Okay. And furthermore, as in the point-to-point setting, so right now I'm talking about time T. Okay. So at time T, the decoder will the destination or the decoder will be basically attempting the recovery of message which was sent at time T minus tau. Okay. Because tau is the delay constraint. So at time T, you'll be looking tau time slots back. So M of T minus tau will the destination will try to recover at time T. So this is a complete figure. So source will take in M of T. It will produce a coded packet excess of T, which will be sent to the relay. Relay will receive YRT, which will be either excess of T or a star. And then relay will do some computations and it will produce XR of T, which is another coded packet. And this coded packet will be sent to the destination. Destination will receive YDT, which will be either again XR of T or a star. And then at time T, destination will attempt the recovery of M of T minus tau. Okay. So now let's look at a rate upper bound for the 3-node set. Okay. So naturally the rate is defined to be K over NR, comma K over NS, the minimum among these two quantities. Recall that the coded packets have size NS, which is the coded packet sent by source, and the coded packet sent by relay has size NR, right? And the message size is basically fixed to be K. So because of that, the rate for the setting is defined to be minimum of K over NR, comma K over NS. So let's try to come up with a quick upper bound, rate upper bound. Okay. So here I have two boxes. So each box denotes a coded packet. So if you look at the first row, that corresponds to coded packets in the source to relay node. Okay. The second row corresponds to coded packets in the relay to destination link. Okay. And each column corresponds to a time slot. So this is time T. Sorry. This is time T. This is time T plus 1. This is time T plus 2, and so on. So basically, this is the coded packet sent by the source at time T. This is the coded packet sent by the relay at time T, and so on. Okay. So that's the meaning of these boxes. And now, let's assume that B burst has occurred in the relay to destination link as follows. Okay. So basically, from time slot tau plus T plus tau minus B plus 1 till T plus tau. So there are B time slots here. So let's assume that in those time slots, there are erasures. All those coded packets in those time slots are erased. Okay. So now let's think about the recoverability of message which is being sent at time m of t. Okay. Since from the point of view of the destination, there are B packets which are getting erased starting from time slot t plus tau minus v plus 1 till t plus tau, right? So basically, the destination is not going to receive any information after t plus tau minus b, right? Which is pertaining to the message packet m of t. So because of that, the destination should be able to recover m of t at this point. So what is this point? So that point is basically the time slot t plus tau minus b, right? So at time t plus tau minus b, this destination should be in a position to recover m of t because all the subsequent packets are anyway erased, right? And now recall that whatever message packets which are being received by the destination is basically forwarded by the relay, right? So if at all destination should be able to recover m of t by time t plus tau minus b, then relay also should have that ability, right? Relay also should be able to recover m of t by time t plus tau minus b, right? So that's a scenario. And now recall on top of that, on the first link, there could be B burst erasures happening. Okay. So basically, effectively, the condition here is the following. Okay. If you look at the source to relay link, it's in fact equivalent to a point-to-point setting with an effective delay, which is tau minus B. Okay. So because of the peculiar way in which I have arranged erasures in the destination link, the relay should be always able to recover the m of t with the delay tau minus b. Okay. So effectively, the delay has become tau minus b, which is theta. And moreover, there could be erasures, burst erasures happening in the source to relay link as well. Okay. So because of that, I can write my rate to be basically min of k over ns comma k over nr, which is obviously less than or equal to k over ns. And now, since k over ns is basically the rate in the first link, right? And as I have just mentioned, the first link is equivalent to point-to-point setting with an effective delay theta, right? Theta is tau minus b. And so now recall our old expression, right? Tau over tau plus b. So instead of tau, I'll put tau minus b, which is theta. So because of that, I have rate less than or equal to theta over theta plus b. So that's the rate upper bound that we have. So now our goal is to construct codes which meet this rate upper bound. Okay. So recall that for the 3-node setting, we need to talk about 2 encodings, right? Because source will be producing coded packets and relay also will be producing coded packets, right? And also from our discussion which we had in the previous slide on the rate upper bound, we just saw that the first link, right? The source to relay link, it's equivalent to a point-to-point setting link with effective delay theta, right? So motivated by that, we are going to use an HT code there, the optimal code which we had for the point-to-point setting, okay, with delay theta instead of tau. And that code plus diagonal interleaving we are going to use for the source to relay. Okay, and relay to destination, what we are going to do is that it's again we are going to use diagonal interleaving, but HT code, the vanilla HT code will not work there, so we need to make some modifications. And that's basically our contribution. So let's look at an example for the 3-node setting. Let's assume b equal to 4 and tau equal to 10. Okay. So right now I'm talking about the encoding which is being done at the source to relay link. So basically how the source is producing the coded packets. That's what I'm going to discuss now. So b is equal to 4 and tau equal to 10. if you recall, so basically, if you look at the source to relay link, it's a point-to-point setting, right? So we need a point-to-point streaming code with effective delay, tau, theta, which is tau minus p, which is 6. Okay. So what we are going to do? So we are going to use a 10.6 HT code plus diagonal interleaving. So what was the HT code? We already saw this generator matrix in one of the previous slides. So we have a generator matrix. Let's say M0, M1, M2, M3, M4, M5 are the message bits, and P0, P1, P2, P3 correspond to the corresponding parity bits. And how are we going to do the diagonal interleaving? So diagonal interleaving will be done like this, right? So if you look at the coded packets which are sent by the source, each column corresponds to a coded packet. Each column corresponds to a coded packet. If we look at the diagonals, each diagonal will be a code word which is coming from the code which has the corresponding generator matrix as given here. Okay. So that's the way we are going to produce coded packets at the source. Okay. So clearly, if you look at the rate of the source, right? So it's going to be theta over theta plus b, which is nothing but 6 over 10.6, and that matches with, so that's the optimal rate, right? Theta over theta plus b. So at least for the source case, we are matching the rate. Okay. So now our goal is that even for the relay to destination encoding also, we should have a rate which is 6 over 10. Okay, so that the scheme is optimal. Okay, so now let's look at what the relay is going to have. Okay, so recall that the source has this HT based HT code, right? 10.6 HT code plus diagonal embedding. That's what the source has used to produce the coded packets, which it's going to send to the relay, right? So now let's assume that in the source to relay link, a burst has happened on time slots t, t plus 1, t plus 2, and t plus 3. Recall that b is equal to 4. So bursts can have length at most 4. Okay. So here these 4 packets are erased. XST, XST plus 1, XST plus 2, XST plus 3. These are all erased. Okay. So now at t plus 4, what will the relay have? At t plus 4, obviously the relay is going to have M4 because it's not erased, right? So relay will have M4. At t plus 5, at time slot t plus 5, relay is going to have M5 because that's also not erased, right? At t plus 6, I have written that.
Hi, Nikhil. So
Yeah.
why M5 is not erased? M5 can be erased, right? The constraint is that not more than 4 can be erased consecutively. But
Yeah,
after
so
M4 is correct, M5 can be erased.
no, so the constraint is that basically all the erasures will be confined to 4 time slots, right? So right now, I'm already saying that M0 to M3 are erased. So which are basically corresponding to time slots T to T plus 3, or already 4 time slots are gone. So no further erasures can be accommodated.
Okay.
So M0 to M3 are already wiped out. T to T plus 3, there is already a burst erasure of length 4, right?
Okay,
In fact,
I just thought that it is only that 4 consecutive, not more than 4 consecutive can be erased. But you are saying that overall, like in this 10, only 4 can be erased.
yeah, so there's one point though. So even though I'm saying that only one burst erasure which span 4 consecutive slots can be erased, even though I'm saying like that, but thanks to the fact that we have a delay constraint in place, right? Because of the delay constraint, we can in fact tolerate many more erasure patterns. In fact, if 2 subsequent bursts are having a guard interval of 2 time slots in between, then for any such pattern, the code can still tolerate. Okay, so
Okay.
that is there, but yeah, so that's another point. I don't want to go into those details, but in this particular example, I'm already assuming that there is a burst which is starting at time t.
Okay.
And since it's a burst erasure, it can go only till t plus 3, right? So,
Okay.
in fact, in one of the next slides, I think I'll be even discussing a case where t plus 5 is time slot t plus 5 is involved, wherein M5 is getting erased. That's also discussed. But in that case, the burst is actually starting at time t plus 2, I guess. T plus 2, t plus 3, t plus 4, t plus
Okay.
5, right?
Yeah, I mean, basically the assumption is that no two bursts like fall in the same T to T plus tau or in 6 slots.
Yeah, something like that. Yeah. So there should
Okay.
be some guard interval, and that guard interval is in fact tau. So in this case, it's theta.
Okay.
Okay. Yeah.
Thanks.
Yeah. So So here obviously M4 is available because it's not erased. M5 is available because it's not erased. And then I'm saying that P0 is available, right? So P0 is available, but instead of P0, I have written here M0. And why is it that? Because recall that whatever code I am diagonally embedding here, it's the HT code, which has that delay property, right? So effective delay here is theta. So every erased symbol, I can recover with the delay theta equal to 6. So here M0 is erased, right? So now if you count the delay, right? So this is 0, 1, 2, 3, 4, 5, 6. This is precisely 6. So at time slot 6, I should be able to recover M0. So thanks to the HT code, right? So because of that, M0 is available. So similarly, even though I am receiving T1, effectively I am getting M1. I can compute M1. Again, because of the fact that I'm using an HT code. Okay, using M4, M5, P0, and P1, I'll be able to compute M1. Similarly, using M4, M5, P0, P1, and P2, I can compute M2. And finally, M3. Okay, so that's what I have written here. So I have M4, M5, M0, M1, M2, M3 available to the relay at time t plus 4, t plus 5, t plus 6, t plus 7, t plus 8, t plus 9. Okay, so that's a scenario. M4, M5, M0, M1, M2, M3. So note that there's some sort of a permutation happening. Even though I sent the messages like M0, M1, M2, M3, M4, M5 in that order with respect to the time slots, because of the erasure, the way these message symbols get manifested at the relay is in a permuted manner. So it's now becoming M4, M5, M0, M1, M2, M3. That's the way in which they are getting recovered at the relay. Okay. So now let's consider another scenario. So here I'm considering bursts which is starting at time t plus 1. So t plus 1, t plus 2, t plus 3, t plus 4, we have erasures. So here M0 is not involved. So it's anyway available at the relay. M5, it's available. P0, it's available. Okay. P1, instead of P1, I can write M1 because, again, thanks to the fact that we have effective delay theta equal to 6 and I'm using an HT code, right? So with delay 6, I can recover all the message symbols. So M1 I can recover at this point. M2 also I can recover at this point, and M3 I can recover at this point. Similarly, I can go through a few more examples, and then I can say the order in which symbols are getting recovered. Okay. This is in fact one of the scenarios where M5 is involved. Okay. So yeah, so let me just go through these figures. Okay, fine. So basically, this is a final observation that I want to make. So depending upon the erasure pattern, okay, relay will have recovered the message symbols in this order. So sometimes it will be M4, M5, M0, M1, M2, M3. Sometimes it will be M0, M5, P0, M1, M2, M3. So basically, there'll be some permutations or mixing which might be happening. For example, here there's a mixing, right? So if you look here, in this case, M4 is missing, in fact. So M4 is missing. So instead of that, there's a P0 coming here, which is in fact a function of M4 and some symbol. Okay, so it involves M4, but it's M4 is not present purely. Okay, we are only getting a mix of symbols. And moreover, there'll be a permutation also happening because M0, M1, M2, M3 are not coming in order, right? So here, for example, M0 is coming, then M5 is coming next, then P0, then M1, then M2, then M3. So all these things can happen. Okay, so message symbols will become available at the relay in a permuted or mixed manner because of the erasures happening in the first link. And moreover, this pattern depends on the erasure pattern itself, right? This permutation will depend on the erasure pattern itself. And now the relay will have to use these message packets, these message symbols, which it has recovered to do the encoding on the subsequent link, right? On the relay to destination link. So now let's talk about the encoding, how relay is going to produce its coded packets, which it's going to send over the relay to destination link. Okay, clearly we need an adaptive coding scheme, right? Because as we have just noted, depending upon the erasure which we see on the first link, which we see on the source to relay link, the manner in which the relay is going to recover the message symbols will vary, right? So there'll be permutation or mixing according to the erasure pattern seen. So depending upon that, our coding scheme also need to change. So we basically need an adaptive coding scheme which depends on the erasure pattern seen in the source to relay link. Okay. So now let's take one specific case where, for example, let's say in the source to destination link, packets T+1, packets sent at T+1, T+2, T+3, and T+4 are erased. Okay, so this is the specific scenario I am assuming. So in this case, if you recall, messages which were getting recovered at the relay was in the following order, right? M0, M5, P0, M1, M2, M3. This is the way in which messages were getting recovered at the relay. Okay, and these messages are available from time T+4 to T+9. Okay, I mean, in fact, M0 is available at time T itself, but I'll be starting a new transmission from the relay only from time T+4. Okay, so that's the way I'm always going to do. So, yeah, so I have these message symbols, right? M0, M5, P0, M1, M2, M3. So let's assume that these are my new message symbols for the relay. Okay, so relay will use these new message symbols for the encoding. So that's why I have introduced a cap. So M0 cap, M1 cap, M2 cap, M3 cap, M4 cap, M5 cap. These are the message symbols which are going to be used by the relay in its encoding. And M0 cap is M0, M1 cap is M5, and so on. Okay. And also, I'm going to use some 10.6 code, 10.6 block code. Okay. And I'm going to diagonally interleave that in the following manner. So as you can see in the figure, I'll be starting a transmission starting from time T+4, and it will end at time T+13. Okay. So if you count the number of code symbols, there'll be 10. So the block length is 10. And the dimension is going to be 6. Okay. So now the question is, can I use a plain 10.6 HT code? Will it work? So let's quickly explore that. So let's assume that we are using a 10.6 HT code there. Okay. So in this case, what would happen? So in this case, so M0 cap is being sent at time T+4, right? And 10.6 HT code is effectively having a delay which is 6. So it can recover M0 cap by time T+10. Because T+10 is T+4 plus 6, right? So it can recover M0 here because M0 cap is nothing but M0. So if you look at here, M0 cap and M0 are just the same. So M0 I can recover by time T+10, which is good because if you remember, M0 was originally sent at time T, and I'm recovering it at time T+10, which is good because tau is the actual delay which we have, which we need to tolerate, right? But now how about M1? M1, was originally sent at time t+1. Okay, so I should in fact recover M1 by time t+11. Okay, so that's the deadline I have for M1. But unfortunately, that will not work here, because if you see here, M1 is in fact M3 cap. Okay, so M1 is coming only here at time t+7. So now, if you go by the HT code, its guarantees that I can recover M3 cap only at time t+13, because t+7+6, which is here. But that may be too late for M1, because M1 I need to recover by t+11, but I am recovering it only at t+13. So the vanilla 10.6 HT code is not going to work. Clearly, we need to do something else. Okay. So what can we do? So, but the one good thing here is that the P0 cap, right? I can recover the M0. M0 I am done, right? So M0 I can recover on time. So because of that, even in my coding scheme, the P0 parity I'm going to fix as in the HT code. Because M0 I was able to recover on time. Only the P1 cap, P2 cap, and P3 cap I will try to alter. P0 cap I will retain as it is, because M0 I am able to recover on time. That's the idea. Okay. So we'll fix P0. Yeah. Parimal?
Sorry, Nikhil, by accident. I'm just switching Zoom.
Yeah, sorry. Yeah. Sure. So P0 cap, I'll fix as it is. So here what I have shown here is the full HT code generator matrix, right? So I am freezing all these columns. So even in our construction, we are going to retain all these columns. All these parts are same. I mean, obviously the initial 6 columns are the identity matrix, and the P0 part also I'm fixing, thanks to the fact that M0 I am able to recover on time. Okay. The remaining 3 columns I need to change. Okay. The current system is not going to work, right? So what change should I make? So in order to see what change should I make, so I'll just look at the last 3 columns which I need to change, and I'll look at the bottom 3 by 3 matrix. Okay, so I'll just focus my attention on. I'll just focus my attention on this matrix here. I'll just focus my attention on this matrix, and I'll try to permute the columns, okay, the last 3 columns, such that it contains an identity matrix. Okay, and I'll explain what do I mean by that in the next slide. So for example, I have permuted the columns, the last 3 columns like this. Okay, so I have moved this column to here and this column to here, and the second column I'll retain as it is. Okay, so when I did that, what happened was the following. I ended up with this matrix. Okay, now if you see here, there's an identity hidden, right? So there's a 1 here, 1 1 1 here. There's an identity matrix here, and obviously, I mean, there's a 1 here, there's a 1 here, but so it's not purely an identity, but I mean, embedded within that submatrix, you have an identity. So that's the idea, right? So I'll permute my column such that this happens. Okay. And now what I'm going to do is the following. I'll ensure that 3 by 3 matrix, right? It's an upper triangular matrix. All the entries below the main diagonal should be 0. So for example, here I have a 1 there, right? So I need to make that 0. So what I'm going to do, I'll make that 0. And that's my matrix. So this is the final matrix. Okay. So all I did was basically I permuted the last 3 columns so that embedded within that 3 by 3 matrix, you have an identity. And then what I did was I made sure that that 3 by 3 matrix is an upper triangular matrix. And that basically gives us our code. Okay. So there's a reason why it works, but that will take more time. So in the interest of time, I won't go into the details, but so this is basically the construction. So now let's quickly see whether it works. Okay. Just a couple of examples we'll see, and so that you'll understand why is it working. Okay. So this is the code that I'm going to use. So it's not purely an HT code, right? Because these three columns I have changed. I have permuted and I have made some ones, zeros, right? So this is the code. And now let's see why this thing works. Okay, so recall that here the message symbol are not the actual message symbols, right? So here the message symbols are M0 cap, M1 cap, M2 cap, M3 cap, M4 cap, and M5 cap, which correspond to M0, M5, P0, M1, M2, M3, etc. Right? So now let's look at a burst which is starting at time. So in fact, if you remember, this actually corresponds to time t plus 4, and this corresponds to time t plus 30. Okay, so now let's look at a burst which is starting at time t plus 4 and spanning time slots t plus 4, t plus 5, t plus 6, t plus 7. Okay, I'm talking about a burst in the second link, relay to destination link. So which means all the red columns are taken out. Okay, and I'm looking at the recovery of M0 cap, which is nothing but M0, and M0, which was originally sent at time t, right? So I need to recover that by time t plus 10. So t plus 10 is actually here. So I can go only till those blue columns. So I have only the 3 blue columns available with me. Okay, because all the initial 4 columns are gone due to the burst duration. And what I need to ensure is that the 0th column is lying in the span of those blue columns, and that's clearly the case, right? In fact, I mean, this is a property of the HT code because the P0 I didn't even change from the HT code, right? So that's clearly true. This column is lying in the span of these 3 columns. That's working. That's good. I mean, it's not surprising because I didn't change the HT code. In the first parity bit was just the same. Next, let's go to another example. So after M0, I'll probably think about decoding M1, right? So which is M1? So M1 is in fact M3 cap, right? So M3 cap is in fact here, right? So M3 cap is here. So T plus 4, T plus 5, like that it's going. So M3 cap was originally sent at, M3 cap is nothing but M1, right? And M1 was originally sent at time T plus 1. So I should recover that by time T plus 11. So this is corresponding T plus 13. So T plus 11 is actually here. So what I need to ensure is that the 4 blue columns, some linear combination of those 4 linear, blue columns should give me 0, 0, 0, 1, 0, 0. Is that true? That's true. Because you can see that in fact, that last blue column is precisely the same as the third column, right? So it's clearly true. So I can recover M1 also by time t plus 11. Similarly, you can talk about, yeah, so M4 and M5 is basically M2 and M3, which is already available with me. And in fact, next you can see that M1 and M1 cap and M2 cap are also available, which will basically give me my M5 and P0. And once I have M5 and P0, I can in fact recover M4 also. So like that we can do. Okay. So let me just take one more example, and so here I'm considering t plus so here I'm considering an erasure which is starting at t plus 5 and ending at
Hello, sir.
Yeah.
Hello, Professor.
Yeah.
So we are overshooting time. So
Sure. Yeah, I'm done. Actually done. So yeah. So here again we can show in a similar manner that all the symbols can be recovered on time. Yeah, that's it. So in general, what happens is that, so since the relay to destination link encoding depends on the erasure pattern seen on the source to relay link, we might have to add some extra header to the relay to destination packets. So that will slightly decrease the rate. But the good thing is that, so we can in fact amortize that thing by increasing the message packet length. Okay, so that way we'll still stay close to the optimal rate. And that's it. Thank you.
So thank you, Professor, for an informative talk. So please free to ask question if you have any. Uh, So, if no questions, thank you. Thank you, Professor, and have a good evening.
Yeah, thank you. Thank you.
Thanks a lot, Professor, for accepting the request and
Yeah.
giving us the talk.
Yeah, thank you. Thank you, Srinivas. Thank you. Thank you, Parimal, Anoop, for joining in.